So when we're dealing with differential equations, one of the common things that comes up is exponential growth or decay, which follows something that we call the law of exponential change. And what this says is that for exponential change or exponential growth or decay, functions, or so things that can be modeled by this sort of relationship, we say that the rate of change of a quantity, whatever is being measured, looks like G, notice Q, quantity, is directly proportional to the quantity itself. So let's talk about what some of that math vocabulary means. So you might have learned about relationships between variables before, so like direct proportions, direct variation, and inverse variation before. I know that I teach it in my Algebra 2 classes. So direct variation or a direct proportion just means that a variable is equal to a constant times another variable. So you can think of like y equals like 2 times x is a direct relationship, a direct variation between y and x. So when we're taking that into the context of rates of change, right, differential equations, it says the rate of change, so dy dx, so the rate of change of a quantity, so that would be dy dx, or y is the quantity, is directly proportional to itself. So it's equal to a constant times the variable that you took the derivative with respect to, that you took the derivative of. So for instance, that's actually the equation I have down below. So solve dy dx equals k times y. So k times y, this represents a direct proportion. That's what that means. Right, so you can see here, like I have dy dx, right? This is the variable that we took the derivative of, and then that same variable shows up on the other side with a constant times it. So that's what a direct proportion relationship is going to look like. So anything that kind of takes this format with a differential equation has a general solution that you can kind of just jump to. So we're going to solve the very general form first, so that way we can always just immediately go to what the general solution curve is going to look like. So we need to separate our variables first. So I'm just going to rewrite it first. So I'm going to multiply both sides by dx to move my x to the other side. And then I'm going to divide both sides by y. So after I separate my variables, I'm going to get that dy over y equals k times dx. And then I can integrate both sides because I only have one variable on each side. Remember that k is a constant. It's just a coefficient, so it's not another variable. So the integral of dy over y, we know that's the natural log of the absolute value of y. And then the integral of a constant, right, we're integrating with respect to x because of the dx, so this is going to be kx plus c. So then we want to solve for y, so to get rid of the natural log, I'm going to rewrite it as an e equation. So this means that y equals e raised to the kx plus c power. And then I'm going to drop my absolute values. Actually, I'm going to keep my absolute values for now, just write it out in 2 steps. I'm going to split up my exponent there, so break it off as a times e to the c instead of a plus c in the exponent. And then I'm going to drop my absolute values when I make e to the c just another constant. So this is your general format of what the solution curve to a differential equation that starts in that same format of like k times y. So if you start with dy over dx equals k times y, the solution curve is always y equals c times e raised to the kx power. And in this case, the c represents the initial value. So that's your value at like x equals 0, or whatever the independent variable is there. So we're going to actually do some application questions with this. So differential equations are great because they're actually used in modeling situations. So there's a lot more like real life applications than just straight up integral problems would have. So that's kind of nice for those of you who are more into like applications of your learning versus just learning for learning's sake. So one thing, and you probably did a lot of questions like this in maybe Algebra 2 when you learned about exponential growth, right? We have like population growth is modeled by exponentials. So we're being told that the population of bacteria in a culture increases from 400 to 600 in 3 hours. We're going to assume the bacteria population P grows according to the rate equation dP dt equals K times P. So we know that it meets that law of exponential change formula that we just went over. So like we know we can jump directly to the solution curve. And we're being told that T is the time in hours. So our variable T just represents time in hours. So we know if we start with this modeling equation, we just saw that the solution curve is then going to be that y, in this case P, is going to equal C times e to the kt. We're just switching our variables y and x out for the variables in this problem. So our initial time, we don't know when it is, but we're going to assume that the starting time is when it's 400. So our initial value, our C value, is going to equal the 400 because that's our starting amount. So now we know that our population is equal to 400 times e to the kt. So this question wants us to find K. So we also know that after 3 hours, right, we have 1,600 bacteria. So we're told that we have the point when T equals 3, P equals 1,600. So we're going to plug those values in. Just going to put the K there. Right, so if I divide both sides by 400 now, right, 1,600 over 400 is going to give me 4 is equal to e to the 3k. So if I rewrite that using natural logs, I get the natural log of 4 is equal to 3k. And then I'm going to divide both sides by 3. So my k value is the natural log of 4 all over 3. You don't want to switch the numbers like I just almost did. So we found our k value. So that was the answer to that question. And we're going to need that because in the second question, they ask how fast is the population growing when there are 3,000 bacteria in the culture. So we want to be careful here that it's asking how fast. So it's asking for a rate of change, right? So it's asking for dP dt, and it says when there are 3,000 bacteria in the culture. So it's asking for the rate of change when P is equal to 3,000. So we're going to write in our evaluation bar, P equals 3,000. And then we know that we're going to go back to this modeling equation, right? dP dt equals K times P. We know that K is the natural log of 4 all over 3. And we're told that our P value is 3,000. So I can reduce that a little bit first. That's going to be the natural log of 4 all times 1,000. So we could leave it like that, or we could go over to our calculators, which is what I'm going to do. So I'm going to do natural log of 4, close my parentheses. My calculator will cooperate. And if I multiply that by 1,000, that's going to be approximately 1,386.294 years. Hours. T was in hours, so we're going to use the right units there. Right, so to put that in perspective, if I divide that by 24, that's almost 58 days. It's just shy of 58 days for it to have 3,000. And I'm really silly about this because I apparently was not reading the question. So we're looking for a rate of change. So we want to make sure the units are correct for the rate of change. So it is increasing. So it's not a t value. I'm going to start over, erase that last sentence from your mind. So this is a rate of change. So it is changing in units of population over the time unit. So this is going to be increasing at 1,386.294 bacteria per hour when there is initially when there is 3,000 bacteria in the culture. Okay, that was a mess. That's okay. We're just going to keep going with it. Okay, so I'm going to do one more question, and another place that this proportional growth kind of shows up with for differential equations is half-life. So radium-226, which is just a type of radium, loses its mass at a rate that is directly proportional to its mass. So that statement right there, directly proportional to its mass, that tells us that if we let m be mass, dm dt is equal to some k value times the mass that's left over. And we're told that its half-life, which that is the wrong form of its, but okay. If its half-life is 1,590 years, and we're starting with a sample of 100 milligrams, we want to first find the formula for m of t. So in other words, we want to find the particular solution to that differential equation. So we know since it's directly proportional, we have this differential equation going on, which we know means that m of t is going to equal some constant times e to the kt. We're told that we start with an initial sample of 100 milligrams, so our initial value is 100. So that tells us that c is going to be 100. And that's the initial value. C is always the initial value because if you plug 0 in for time, right, e to the 0 is 1, so it just cancels out and you get the initial value back. So now we're told that the half-life is 1,590 years. So if we start at time, right, these are going to be t, comma, m points. At time 0, we start with 100 milligrams. And after a half-life, we would have half of that left. So after 1,590 years, we would have 50 milligrams left. So they actually do give us enough information to solve for the to solve for the k. So you need 2 points in order to fully solve the model because you need 1 point to solve for the c, the initial value, and then you need another point in this situation to solve for the k. So I'm going to plug those values in. So my mass is 50. My initial value is 100, not an equal sign, times e to the k times 1,590. So if I divide both sides by 100, I get 1/2 equals e to the 1,590k. Rewrite that using natural logs. And then divide both sides by 1,590 to get k. So my k value is the natural log of 1/2 all over 1,590. Which tells me that my overall model then is m of t equals 100 e to the, I'm going to write this as t times the natural log of 1/2 all divided by 1,590. So then we want to know how many milligrams of the sample will remain after 100 years. So we want to know what is m of 100. Right, so we get 100 e to the 100 times the natural log of 1/2 all over 1590 power. And then you're just going to go and type that into your calculator super carefully. So 100 times e, make a fraction in the exponent. We got 100 times the natural log of 1/2 all over 1,590. So that's going to be approximately 95.734 milligrams left. Right, just typing that straight into my calculator. And so since we have the model, we can find how much is left after any given amount of time. We can also solve to see how long will it take for us to have a certain amount left. So now they're asking kind of opposite. We want to know the time that it's going to take for there to be 4 milligrams left. So I know that my model, just to write it down here, right, using that same equation that we already came up with, now I want to know when it's going to equal 4. So if I divide both sides by 100, I get 1 over 25 equals e to the t times the natural log of 1/2 all over 1590. Now if I rewrite this using a natural log, I get the natural log of 1 over 25 equals t times the natural log of 1/2 all over 1590. I'm just kind of pulling the t out to the front. So then if I want to solve for time, I would multiply by the reciprocal. So I would do 1590 times the natural log of 1 over 25 all over the natural log of 1/2 is going to equal my time. And then if I just go to my calculator and type that in super carefully, I got ln of 1 over 25, and then divide that by the natural log of 1/2. So it's going to take about 7,383.731 years